In this video, we're going to look at more limits at infinity. What happens as x approaches infinity? So let's begin by looking at these two statements. We've got the limit of f of x as x approaches infinity, which is equal to some constant L. So L is a number like 2 or 10. And then we also have here the limit as x approaches infinity as the limit of f of x as x approaches negative infinity equaling L. Both of these situations are essentially the definition of a horizontal asymptote. So we can picture this graphically. If we have x approaching infinity, the function will limit off to L. That could look like that, or it could look like this. In any event, we have ourselves a horizontal asymptote, and the same would be true as we go out towards negative infinity as well. So the conversation about limits at infinity is a conversation about end behavior. And by end behavior, we just mean what's going on as we go out the ends of the graph. So sometimes we have functions that go up to positive infinity. Sometimes there are functions that go down to negative infinity. Sometimes there are horizontal asymptotes. But every function, as you go out to infinity or negative infinity, is doing something. It's going somewhere. So that is what we are trying to identify when we talk about limits at infinity, the end behavior of the function. So let's look at some examples. A simple example for starters. The limit of 3x as x approaches infinity. If we try direct substitution here, as we have tried with everything up to this point, we end up with a statement 3 times infinity, and 3 times infinity is equal to infinity, and this is the correct answer. It is infinity, and we can think of that making sense graphically because this function is a line that has a slope of 3, and so it's going up, and so as you go out to the right, the function is going up towards infinity. So there's our line. As x goes to infinity, our function is going to infinity as well. What about this one? The limit of the function 1 over x as x approaches infinity. If you try plugging infinity in using direct substitution, you end up with this statement, 1 divided by infinity. Now, 1 divided by infinity is kind of weird because infinity isn't a number, it is a concept. So you've got to think about this conceptually. What's happening if you take 1 divided by infinity, which means a huge number? And if we can approximate this by plugging in a really, really big number, we will see that the outcome is a really, really tiny number. So because we're dealing with a limit and we don't care about what's happening at the specific point, but as we get really close to a specific point, and in this case our point is infinity, so we're trying to just get infinitely close to infinity, which is kind of weird. This is going out to 0. It is becoming 0. It's becoming infinitely close to 0. And you should be familiar at this point with the shape of this graph, this rational function, and we can verify that we're correct. As x approaches infinity, here we go. We're going out in the positive x direction, and the height of these points, the y values, are becoming infinitely small, making our answer of 0 make some sense. So far, those ideas should be familiar to you. You should feel good about that. We've kind of covered that ground already. But things get weird when we look at a function like this, and there's one trick that I'm going to show you right now that's going to be the trick that you're going to pull out frequently when dealing with limits as x approaches infinity. If you look at this example and you consider doing what we've always done and plugging in infinity, you end up with a statement of infinity plus infinity divided by infinity, which ultimately is infinity divided by infinity, which is indeterminate. You have indeterminate form, so you've got to do something algebraically to change it. So here's the tip. Unlike factoring and canceling stuff out, which in this case would be difficult, when you encounter infinity divided by infinity, when you encounter that indeterminate form, you're going to divide every term in the expression by the highest powered x term from the denominator. Whoa. So let me show you what that means. I'm going to look at the denominator and look for my variable x and pick out the one that has the highest exponent, which in this denominator is x squared. This guy doesn't even have an x, so x squared is the highest powered x term from the denominator, and I'm going to divide this guy and this guy and this guy and this guy by it, and when that happens, we're going to see something good happen. So here we have our new limit expression where I have divided every term by x squared. I haven't simplified anything yet. I'm just showing each one of these four terms being divided by the highest powered x term from the original denominator. And next we're going to simplify this and see what it does. So on the numerator, the x squareds cancel out. This x will cancel out with one of these x's, so I'm left with 20 over x. These x squareds will cancel out, leaving me with 4. And then 9 divided by x squared will not simplify. Now that we've done this, let's try direct substitution again and see what happens. We're going to plug infinity in, and we're going to plug in infinity for this x as well. So this is where we need to think about what we are saying. When you plug infinity in for that first x and you get 20 divided by infinity, we need to think about the example that I first showed of 1 over x. We need to ask ourselves, what's happening as you take this limit? You're getting 20 divided by a huge number, and so the limit of this thing is approaching 0 for the same reason that 1 over x approaches 0 as x approaches infinity. Using the same logic, 9 divided by infinity squared, 9 divided by a massive number like 24 billion or 97 trillion, if you think of that, is going to get infinitely close to 0. So again, this will become 0. And this leaves us with the simple answer of 3/4. Alrighty, here's another example. If we try direct substitution, plug infinity in, you get 20 times infinity squared minus 3 times infinity divided by another infinity. This becomes infinity over infinity, which is indeterminate. So we're going to use the same trick. We're going to start in the denominator and ask ourselves, what is the highest powered x term? And it is x to the power of 5. So our technique is going to be to divide every single one of these 5 terms, term 1, term 2, term 3, term 4, term 5, by x to the power of 5. So here we are showing every term divided by x to the power of 5. And now we can simplify this. If we start with the easy ones on the denominator, x to the power of 5 divided by x to the power of 5 leaves us with 3. X squared divided by x to the power of 5 is going to leave us with x cubed on the denominator. And if you're wondering why, just remember properties of exponents. X squared divided by x to the power of 5. We subtract 2 minus 5 to get x to the negative 3. Or another way to think of this is that x squared is x times x divided by x to the power of 5, which is x times x times x times x times x. These guys cancel, leaving us with x cubed on the bottom and a 1 on the top. So 1 over x cubed. So we've got 4 over x cubed plus 5 divided by x to the power of 5 can't simplify. On the numerator, again, x squared divided by x to the power of 5 leaves us with x cubed on the denominator. And x divided by x to the power of 5 is going to leave us with x to the power of 4 on the denominator. And now we go ahead and try plugging infinity into all of these things and see what happens. 20 divided by infinity goes to 0. 3 divided by infinity goes to 0. 4 divided by infinity goes to 0. 5 divided by infinity goes to 0. We end up with 0 minus 0 all over 3 minus 0 plus 0, which is equal to 0 divided by 3, which is not an indeterminate form. It exists, and the answer is 0. So this would be an example of a horizontal asymptote at 0. Graphically, I don't know what that function looked like, but I do know that as we go way out here to positive infinity, the function will be approaching 0.